And good morning. Let's take a look a few more electric field problems for today. So a small plastic bead has a mass of 15 milligrams. Let's draw that on our table. And you know that little plastic beads and little styrofoam beads sometimes pick up a charge. And this one it says is 10 nanocoulombs. Then it says we're going to have a glass rod. And it has a charge of positive 10 nanocoulombs. And because it's positive, notice that the electric field lines, just remember, go out from the positively charged rod. But it is positive, this is negative, the bead will be attracted. Because remember, those lines show the direction a positive test charge would move. So let's see a few things we're going to calculate. And sorry, it kind of goes into the drawing there. Calculate the electric field strength of the rod. Calculate if there's any force on the bead. And then we're going to find out if the bead will leap off the table. So for part A, getting the electric field strength, it's really pretty easy. It's just E equals KQ over R squared. You might say, why didn't you use the F over Q? We can't use that yet. We don't know anything about the force. So K is that 9 times 10 to the 9th. Now remember, it was 10 nanocoulombs, and nano is 10 to the minus 9th. So I'm getting the 10 to the minus 9th. And here's R squared. So we get E is 9 times 10 to the 5th newtons per coulomb. And remember, electric field strengths are really, really large. Now to get the force, we'll use the E is F over Q. And I just took the liberty of rearranging it, but I'll remind you here. E equals F divided by Q. So we just substitute. 9 times 10 to the 5th, which we got in the previous part, and 10 to the minus 9th is the charge. So it's not a very big force. 9 times 10 to the minus 3rd. Now, the question C is, will it leap off the table? If we look at the bead, and we do a free body diagram, didn't you miss them? There's our free body diagram. The bead is mg, and there is a force from the electric field pulling upward. So we have to see which is greater. So mg is 15 times 10 to the minus 6 because it was milligrams to kilograms. I think that should be superscript, but I'll fix that later, times 9.8. So mg is 1.4 times 10 to the minus 4th. That's going down. In fact, let's draw it on the picture here. 1.47 times 10 to the minus 4th. And this is 9 times 10 to the minus 3rd newtons going up. 10 to the minus 3rd is stronger than 10 to the minus 4th. Yeah, this bead will leap off the table. In fact, if we want to, we can subtract those two numbers and get the net force. And one thing you're going to see in some of the homework questions is they might even ask for the acceleration. And we're actually just going all the way back to the second law. F equals ma. So acceleration would be F over m. So if we wanted to, we're not going to do it right now, but we could get the acceleration of the bead. And if I went a little too fast, don't forget, you can always go back and rewatch any of these videos or move the little slider to see if you missed something. Now let's try another problem. We're going to have a copy machine with the toner particles, and this is how they work. So we know the toner particle, and they tell us the mass. And it's really the same kind of thing, where we have a little particle here. We're going to have an electric field trying to exert a force on that charge to lift it up. So let's see what we know. Each particle carries 20 electrons. So just to remind ourselves, what that's going to mean is the charge will be 20 times the charge of an electron, which if we remember is 1.6 times 10 to the minus 19th coulombs. And I have all this on the next slide, so don't worry if I'm going too fast. But they're saying the copier has to overcome twice the weight of the particle, I guess, to pick it up. So let's see what we can do for the force. We want the force to be twice the weight. So the electric field would have to be 2 times mg. So 2, they gave us the mass of the particle, and they give us gravity. And the charge is 20. Now that 1.6 times 10 to the minus 19, I have the more advanced one, 1.602, the more precise number, times 10 to the minus 19, will tell us the electric field that we need, and it's 5,500 newtons per coulomb. And that's a pretty strong electric field, but it's not impossible. Now we'll do just one more quick one. Point Q has an electric field strength of 40 newtons per coulomb, a distance of 30 centimeters away. Here's Q. Now we want to know the magnitude at 60 centimeters. Now we are at 40 centimeters away. Oh, excuse me, that's 30 centimeters, and it's 40 newtons per coulomb. And we want to know, well, what if we go twice as far? Now you might think, oh, well, it's just 20. We're twice as far. It should be half. But don't forget, what we're doing is it's r squared. So let's see what's going on. E equals kq over r squared. Now we have a couple of options here. I think we're going to solve it for q. So q is e r squared over k. Now, the q doesn't change. Let's call this E1 and R1. So even when it's further away, now the electric field is going to be less, but q does not change. So what we can do there is set them equal to each other. E1 R1 squared over k is E2 R2 squared over k. Now watch, the k is going to cancel. So let's see. 40 and R1 is 0.3 squared equals E2 times 0.6 squared. So E2 is 40 times 0.3 squared divided by 0.6 squared. And that's one I'm not going to do on my own. I'm going to need a calculator here. There we go. There's my calculator. So let me take a second and calculate it. 40 times 0.3 times 0.3. So that gets me a top of 3.6. And you'll have to excuse, I don't have a calculator here handy, or a scientific calculator. I'm just using a regular one on my tablet here. That's 0.36. And let's see what that is. 36, or 3.6, excuse me, divided by 0.36 is 10. So you can see, net newtons per coulomb, that we doubled the distance, but when you double the distance, the electric field goes down by a quarter. Now why is that? Well, 1 over 1 is 1. And that's squared. But if I double the distance, it's now 1 over 2 squared, which is a fourth. So a fourth of 40 is 10 newtons per coulomb. And that's it for this video.